Deep under the French-Swiss border, the world's most powerful machine just produced a result that physicists are struggling to explain. The Large Hadron Collider found particles breaking rules we considered unbreakable. We are talking about rules that hold the entire structure of reality together. Today we go inside CERN, through the W boson crisis, the muon anomaly, and the terrifying possibility of a fifth force, to find out what they actually found. If you enjoy this kind of content, subscribe and leave a like. Pay attention. The alarm did not go off. No lights flashed, no sirens. But on a Tuesday morning, in the control room beneath the French-Swiss border, a physicist stared at a screen and felt her stomach drop. The numbers were wrong. Specifically, they were too wrong to be an accident. She was looking at data from one of the most precise experiments ever run inside the Large Hadron Collider, the massive particle accelerator buried 300 feet underground near Geneva, Switzerland. The experiment was measuring how often a specific particle decayed in a specific way. The answer was supposed to match the prediction exactly. It had matched for decades. Every machine, every country, every team that had ever tested it got the same result. This time, it did not match. The gap was small, tiny even. If you tried to express it as a fraction, it would disappear into the decimal point. But in physics, a gap that small is enormous. A gap that small means something is happening that the rulebook says is impossible. She called her supervisor. Her supervisor called the team lead. The team lead looked at the screen for a long time and said nothing. That moment happened not once, but several times over the past decade at CERN. Different experiments, different teams, different particles, same problem. The rules of physics kept producing results that the rules of physics said should never appear. To understand why that is terrifying, you have to understand what those rules actually are. Physics runs on a system called the Standard Model. Scientists built it piece by piece over about 50 years. It describes every particle that exists, every force that controls them, and every interaction between them. Gravity, electromagnetism, the forces that hold atoms together, the forces that tear them apart. All of it fits inside this one framework. And for 50 years, every experiment ever run confirmed it. Every prediction it made turned out to be correct. Scientists called it the most tested theory in human history. That kind of track record makes you confident. It makes you assume the model is complete. Then the cracks started appearing. The first one barely made the news. A team running an experiment called LHCb noticed that a particle called the beauty quark was decaying at the wrong rate. Beauty quarks live for an incredibly short time before they split into lighter particles, and the standard model predicted exactly how often each type of split should happen. The data said something different. The difference was subtle, but it was consistent. Run the experiment again, same result. Run it a third time, same result. In science, a result that keeps repeating stops being noise. It starts being a signal, and this signal was pointing somewhere the standard model had no room for. Now, scientists are careful people. They do not declare a crisis over one strange number. They look for every possible mistake first. Bad equipment, calculation errors, bias in how the data was collected. The LHCb team spent months checking every piece of their setup. They found nothing wrong. The data was clean. The result was real. Something was happening inside those particle collisions that 50 years of physics could not explain. One senior physicist compared it to building a house for decades, checking every brick, every beam, every nail, and then watching one wall vibrate on a perfectly still day. The house looks fine, the instruments say nothing is wrong, and yet the wall moves. That vibrating wall is what CERN found, and the deeper they looked, the more walls they found moving. The beauty quark result was strange on its own, but when scientists started pulling the thread, they found it connected to something far bigger, a problem sitting at the center of how matter itself is supposed to work. What that problem is, and why it changes everything, starts with the machine. Picture the longest tunnel you have ever been in. Now, make it circular. Stretch that circle until it is 17 miles around, wide enough that you could fit the entire island of Manhattan inside the loop. Bury it 300 feet underground. Line every inch of the walls with superconducting magnets cooled to -456 degrees Fahrenheit, colder than the surface of Pluto. Fill the tube with a vacuum so empty it has less air inside than the surface of the Moon. That is the Large Hadron Collider. Inside this machine, scientists fire two beams of protons in opposite directions. Each beam accelerates until it reaches 99.999% of the speed of light. At that speed, a proton completes 11,000 laps around the 17-mile ring every single second. Then, at 4 specific points along the ring, the beams cross. The protons collide. Each collision releases an amount of energy so concentrated it briefly recreates conditions from a fraction of a second after the Big Bang. The temperature at the collision point reaches several trillion degrees, roughly 100,000 times hotter than the center of the Sunday. For one tiny instant, the rules of physics that govern our everyday world stop applying. Matter dissolves. Particles that do not exist anywhere else in the modern universe blink into existence for a fraction of a second before falling apart. And in that falling apart, the secrets come out. The Large Hadron Collider runs about 40 million collisions per second. 40 million. Detectors the size of apartment buildings record what comes out of each one. These detectors weigh more than the Eiffel Tower. They measure particles moving at near light speed with precision down to millionths of an inch. The data those detectors produce in a single year would fill more than 1 million laptop hard drives. Scientists spend years sorting through it, looking for anything that should not be there. Here is why the machine matters beyond its size. Every particle that exists carries a kind of fingerprint, the way it decays, the angle it travels, the energy it releases when it breaks apart. All of that tells you exactly what it is. The standard model predicted all of those fingerprints decades before scientists had machines powerful enough to check them. And for decades, every fingerprint matched the prediction perfectly. The Large Hadron Collider is powerful enough to produce rare particles in large enough numbers that scientists can now run statistical tests with real confidence. They are not guessing. They are counting hundreds of thousands of the same event and measuring how often each outcome appears. That level of precision is what makes the anomalies so alarming. When a fingerprint does not match, it means one of two things. Either something went wrong in the measurement, or something exists that the model does not account for. Something invisible, something that reached into the collision and nudged the result. The machine cannot see that invisible thing directly. No machine can, but it can see its shadow. Every time a particle behaves differently than predicted, it leaves a trace, a number that is off by just enough, a decay that happens a fraction too often or not quite enough. Scientists call these traces anomalies, and over the past decade, the anomalies at CERN have been piling up in ways that no single equipment error or calculation mistake can explain. The beauty quark anomaly was one, the muon anomaly was another. The W boson result shook the field entirely. Each one seemed isolated at first. Then scientists started noticing they all pulled in the same direction, towards something the standard model has no slot for. To understand what that something might be, you first need to understand what the standard model actually built, and where it always knew it was incomplete. Imagine you are handed a rulebook for a game you have never played. The rulebook is 600 pages long. Every rule connects to every other rule. You read it cover to cover, and it makes perfect sense. You play the game 1,000 times, and the rulebook predicts every outcome correctly. You hand it to someone else, they play 1,000 more times, same result. Everyone on Earth plays the game, same result. You start to believe the rulebook is complete. Then one day, in one game, something happens that the rulebook has no explanation for. That is exactly where physics stands right now. The standard model is the rulebook. Scientists assembled it over roughly 50 years, starting in the 1960s and reaching its most complete form by the 1990s. It describes 12 fundamental particles of matter and 4 forces that control how those particles interact. It predicted the existence of particles before anyone had the technology to detect them, and when the technology arrived, those particles were exactly where the model said they would be. The Higgs boson is the most famous example. The model predicted it in 1964. Scientists spent nearly 50 years and built the most expensive machine in human history to find it. They found it in 2012, exactly where the math said it would be. That kind of accuracy builds trust. It made the standard model feel bulletproof, but even its creators knew it was incomplete. They knew it from the start. The standard model has no explanation for gravity. Gravity is the most obvious force in the universe, the one you feel every second of your life, and the model that describes all other forces simply leaves it out. It works anyway, because gravity is so weak at the particle scale that it barely matters in those experiments. But leaving out gravity means leaving out a piece of reality. The model also has no explanation for dark matter. Scientists know dark matter exists because they can see its gravitational effect on galaxies. Galaxies spin in ways that only make sense if there is far more mass than we can see. But the standard model has no particle that could account for it. No slot, no placeholder, and the model cannot explain why the universe is made of matter. Equal amounts of matter and antimatter should have been produced at the Big Bang. Equal amounts should have annihilated each other instantly. The universe should be empty. The fact that matter won, that stars and planets and humans exist, has no explanation inside the current model. These gaps were known. Scientists assumed they would eventually extend the model to fill them. Then came the anomalies. The anomalies are different from the known gaps. The known gaps are things the model simply does not address. The anomalies are places where the model makes a specific prediction and the experiment produces a different answer, a direct contradiction. Direct contradictions are far more dangerous than gaps. A gap says the map is incomplete. A contradiction says the map is wrong. Scientists spent decades adding to the map. They tested it from every angle. They spent billions of dollars and decades of work confirming every corner of it. The idea that part of it might be wrong is not just scientifically significant. For the people who built their careers on it, who staked their reputations on it, it lands like a punch. One physicist described it as looking at a photograph of your house and realizing the shadow in the corner does not match anything in the yard. The house is still standing, but something is casting that shadow. The first time scientists started suspecting the shadow was real came right after the greatest triumph the standard model ever had. July 4th, 2012 started as a celebration. Scientists packed an auditorium at CERN. Some had flown in from across the world. Peter Higgs, the physicist who first predicted the particle nearly 50 years earlier, sat in the front row. He was 82 years old. He had spent his entire career waiting for this day. The announcement came with data, graphs, and measured scientific language. But everyone in the room understood what it meant. They had found the Higgs boson, the last missing piece of the standard model, the particle that gives all other particles their mass. Peter Higgs wiped tears from his eyes. The Higgs boson matters because without it, nothing should have mass. Mass is the property that makes matter feel heavy, that makes objects resist being pushed, that keeps you in your chair instead of floating off. The Higgs field, the invisible field the boson is associated with, spreads through all of space. Every particle that has mass gets it by moving through that field, like a person pushing through a crowd. The more a particle interacts with the field, the heavier it becomes. Before 2012, scientists knew the field had to be there because the math demanded it, but they had never directly detected the boson, the ripple in the field that proves the field exists. Finding it closed the last open question in the standard model. That should have been the end of a chapter. Instead, it opened something unexpected. When scientists analyzed the Higgs boson data in detail, They started measuring its properties with extreme precision: how it decays, how often, what particles it produces when it breaks apart. Every measurement was supposed to confirm the Standard Model's predictions. Most did, but a few were slightly off. At first, the scientific community treated this as measurement uncertainty. The Higgs boson is hard to detect. The signal is buried under enormous amounts of background noise. Getting precise numbers takes years of data collection. Slight deviations early on were expected to smooth out as more data came in. Some did smooth out, others held. And then, running parallel to the Higgs measurements, other experiments started reporting their own small deviations. A pattern began to emerge. Separate experiments, separate teams, separate parts of the machine, all finding small but consistent gaps between prediction and result. Scientists have a threshold for when a result counts as a real discovery. They call it 5 sigma. That means the result is so far from what random chance would produce that the odds of it being a fluke are less than 1 in 3.5 million. The Higgs boson crossed that threshold. Several of the anomalies that followed came close. Getting close to 5 sigma across multiple independent experiments is the kind of thing that keeps physicists awake at night. The Higgs discovery was supposed to be a finish line. Teams disbanded, funding redirected. The story of the Standard Model felt complete. Then the data started whispering that the story had another chapter, a darker one. The Higgs boson itself became a tool. Scientists used it to probe deeper into the structure of the model, looking for cracks. And the cracks, when they appeared, led straight back to a question the model never answered. A question about what matter actually is and why anything exists at all. That question has been sitting at the center of physics for decades. The anomalies are starting to suggest the answer involves something the model has no room for, something hiding just outside the edge of what we can see. Hold your hand in front of your face. It looks solid. It feels solid. If you press your fingers together, they do not pass through each other. Every instinct you have tells you your hand is a dense, continuous object made of something real. Every instinct is wrong. Your hand is almost entirely empty space. An atom is the basic building block of matter. If you took a single atom and blew it up to the size of a football stadium, the nucleus at the center would be the size of a marble sitting on the 50-yard line. The electrons orbiting around it would be too small to see. Everything else, the entire rest of the stadium, would be empty. Your hand is made of billions upon billions of atoms. Each one is almost entirely empty. The reason your fingers do not pass through each other is electromagnetic repulsion. The electrons in your hand's atoms push back against the electrons in the other hand's atoms. You are not touching anything. You are being repelled by an invisible force. That is matter, and it goes deeper. Atoms are made of protons and neutrons in the nucleus, surrounded by electrons. For a long time, scientists thought protons and neutrons were fundamental, the smallest things that could exist. Then experiments in the 1960s revealed that protons and neutrons are themselves made of even smaller particles called quarks. A proton contains 3 quarks. They are bound together by a force called the strong nuclear force, carried by particles called gluons. The quarks inside a proton are moving constantly. They are exchanging gluons back and forth at incredible speeds. The energy of all that motion is so large that it actually contributes more to the proton's mass than the quarks themselves do. The thing you think of as the solid core of matter is mostly the energy of motion trapped in a tiny space. That idea alone should make you stop for a second. The solid world around you is mostly the frozen energy of particles that have never, in the entire history of the universe, stopped moving. Now, here is where CERN enters the picture. When the Large Hadron Collider smashes protons together at near light speed, it does not just break them apart. It converts their kinetic energy, the energy of their motion, into new particles. Energy becomes matter. That is what Einstein's most famous equation actually means in practice. Energy and matter are the same thing, expressed differently. The particles that appear in those collisions exist for unimaginably short periods of time. Some survive for less than a trillionth of a second, but in that tiny window, they carry information about forces and fields and interactions that normally stay completely hidden inside stable matter. Scientists read that information through the detectors, and the information kept pointing to something unexpected. Some particles were interacting in ways that suggested a hidden influence, something reaching into the collision from outside the standard model's boundaries. To understand what that hidden influence might be, you have to understand its opposite, the shadow version of matter, the thing that should have destroyed everything the moment the universe began. 1 second after the Big Bang, the universe was a fireball. Inside that fireball, energy was converting into matter at an incredible rate. Particles were appearing out of pure heat and light. And here is the part that should disturb you. For every particle of matter that appeared, an identical particle of antimatter appeared alongside it. Antimatter is real. Scientists make it in laboratories. They have made it at CERN. It behaves exactly like regular matter in almost every way, except for one property. When a particle of matter meets its antimatter counterpart, they annihilate each other. Both disappear in a flash of pure energy. Every proton should have had an antiproton to cancel it out. Every electron should have had an anti-electron. Every quark, an antiquark. The math is clean. Equal amounts of each. Total annihilation. The universe should have been left with nothing but light. You exist. Which means something went wrong with the math. Somewhere in the first second of the universe, matter won. The victory was tiny. For every 1 billion antimatter particles, there were 1,000,000,001 matter particles, a difference of 1 in a billion. That tiny surplus is everything. Every star, every planet, every galaxy, every human being is built from that leftover one. Scientists call this imbalance matter-antimatter asymmetry. The standard model acknowledges that it exists. It even predicts a small amount of it through a mechanism called charge parity violation. But when physicists calculate exactly how much asymmetry the standard model allows, the number comes out far too small. The asymmetry in the model is billions of times weaker than what would have been needed to produce the universe we live in. The universe exists because of an imbalance the standard model cannot fully explain. CERN was designed in part to hunt for the answer. Scientists built a dedicated experiment inside the collider to study antimatter directly. They trap anti-hydrogen atoms, the antimatter version of the simplest element, and measure their properties with extreme precision. The goal is to find some tiny difference between matter and antimatter that the model missed. Any difference at all would be a clue. So far, antihydrogen looks nearly identical to regular hydrogen. Nearly. There are hints. Small statistical differences that keep appearing at the edge of measurement precision. Scientists are careful about calling them real. They need more data, more runs, more time. But the hints keep showing up, and one particular set of experiments, not at CERN directly, but using particles produced in collisions there, started producing results that shook the entire community. Not hints, full-scale anomalies. Numbers so far from the prediction that they could not be explained by measurement error. The question of why matter won over antimatter is connected to the same thread that runs through every anomaly CERN has found. They all point toward the same gap, the same invisible something that the standard model has no room for. Understanding what that something might be requires looking at what happens when particles decay. And the specific type of decay that set off the loudest alarms at CERN involves a particle called the beauty quark. Its behavior should have been predictable. It was anything but. Scientists know matter won. They just have no complete explanation for how. That gap is one of the deepest unsolved problems in all of science. And it is personal in a way most physics problems are not, because the answer to why matter won is the same as the answer to why you exist. Why anything exists. Why the universe is a place with stuff in it rather than an ocean of light. The standard model gives scientists a partial answer through a mechanism called charge parity violation. Here is what that means, in plain terms. When certain particles decay, they do not treat matter and antimatter identically. They show a slight preference. One version of the decay happens a little more often than the other. That tiny preference is called charge parity violation, and it is one of the conditions that could allow matter to pull ahead of antimatter in the early universe. Scientists first confirmed charge parity violation in 1964 using particles called kaons. It was a Nobel Prize-winning discovery, but when they measured exactly how much violation the kaons showed, the number was too small, way too small, billions of times too small to explain why the universe ended up with the matter surplus it has. So they looked for other particles that might show more of it. Certain particles containing bottom quarks, also called beauty quarks, were predicted to show much stronger charge parity violation. That made them a primary target. Scientists built the Large Hadron Collider's dedicated beauty quark experiment called LHCb specifically to measure this, and they found charge parity violation in beauty quarks, a significant amount, more than in kaons, but still not enough, still not anywhere close to the level needed to explain our universe. Every time scientists measure charge parity violation in a new particle and come up short, the same question gets louder. Where is the rest of the asymmetry coming from? What produced enough imbalance to leave the universe with a surplus of 1 in a billion? One possibility is that the asymmetry came from a source the standard model cannot see. A new particle, a new force, something that was active in the early universe and produced a huge charge parity violation that no current experiment can detect directly. That hidden source would leave no trace today, except one. It would leave a universe full of matter, which is exactly what we observe. Scientists at CERN began hunting for that hidden source, not by looking for it directly, but by looking for its effects on particles they could detect. If something beyond the standard model influenced the early universe, it likely also influences particles today, just in very small and hard-to-measure ways. That is the logic behind the beauty quark experiments. Measure enough beauty quark decays with enough precision, and any hidden influence will eventually show up as a statistical deviation. It showed up. In 2019, the LHCb collaboration published a result that made the physics world take a hard breath. Beauty quarks were decaying into electrons and muons at different rates. The standard model said those rates should be identical. They were not. The gap was small but consistent, and it pointed directly at a force or particle outside the model. The team called it a hint. Over the next 2 years, that hint grew louder. And then, from a completely different direction, a different machine confirmed that something was wrong with the same part of the theory. The LHCb detector sits in a cavern underground, and it was built for one specific job: track the beauty quark, measure everything about how it lives and dies, do it billions of times until the statistics are so strong that no one can argue with them. The beauty quark earns its name by being unusual. It is heavy by quark standards. It lives longer than most unstable particles, long enough for detectors to watch it travel a tiny distance before it falls apart. That makes it measurable in ways other quarks are not, and the way it decays carries information about which forces influenced it during its brief life. The standard model makes exact predictions about beauty quark decays. It says the quark should decay into an electron a certain fraction of the time, and into a muon a certain fraction of the time. An electron and a muon are both members of a family of particles called leptons. They carry the same electric charge. They behave almost identically, except that the muon is about 200 times heavier. The standard model treats them as interchangeable in decay processes. Same charge, same force interactions, different mass. The mass difference matters for some calculations, but for the specific decays the LHCb was measuring, the model predicted the rates should be equal. The decay into electrons and the decay into muons should happen at exactly the same frequency. They did not. The LHCb collaboration measured this ratio across hundreds of millions of decays. They found that the decay into electrons happened more often. The difference was small in absolute terms, but in statistical terms it was significant enough to demand an explanation. The property being tested has a name. Scientists call it lepton universality, the idea that leptons, regardless of which type they are, experience forces in the same way. Lepton universality is built into the Standard Model as a fundamental principle. It is not a guess. It is a structural requirement. If it is violated, the model's framework cracks at the foundation. The LHCb result was a violation of lepton universality. The team checked their equipment. They checked their analysis. They ran the numbers through independent methods. The result held. They published it as a 3.1 sigma result, meaning the odds of it being a random fluctuation were about 1 in 1,000. Strong enough to take seriously, not yet strong enough to claim a discovery. The physics community reacted the way it always does to a serious anomaly. Half the field started looking for ways to explain it within the existing model. The other half started building theories about what could cause it outside the model. Then, in 2021, LHCb updated the analysis with more data. The results shifted. The new analysis suggested the deviation was smaller than initially measured. Some scientists called it resolved. Others pointed out that the new analysis used different methods and that the question was still open. Then, in 2023, the LHCb published a deeper analysis combining multiple decay channels. The overall picture of beauty quark behavior remained inconsistent with the Standard Model across several measurements simultaneously, even if individual numbers shifted. The debate about whether any single measurement constitutes a violation is ongoing. What is harder to debate is the overall pattern. Multiple independent measurements, multiple decay channels, multiple teams, all showing small but persistent gaps in the same direction. A pattern like that does not appear from noise. It appears from a cause, and whatever that cause is, it interacts with leptons, which means the next piece of the puzzle involves understanding what leptons actually are, starting with the strange ones raining through your body right now. 6 types of quarks exist. Scientists call those types flavors. That sentence is completely accurate and completely absurd. Subatomic particles do not have flavors in any way connected to taste. The word was chosen informally in the early days of quark physics, and it stuck. Science, like everything else, has its strange traditions. The 6 flavors are called up, down, charm, strange, top, and bottom. Up and down quarks are the ones that make up protons and neutrons, the particles inside every atom you have ever touched. The others are heavier, unstable, and only appear when particles collide at high energy. Each quark carries a fractional electric charge, which was one of the most surprising discoveries in particle physics. For most of history, scientists assumed electric charge only came in whole units. Quarks broke that assumption. An up quark carries 2/3 of a positive charge. A down quark carries 1/3 of a negative charge. Combine 2 ups and 1 down, and you get a proton with exactly 1 full positive charge. The rules for how quarks combine are strict. They can only form groups of 2 or 3, held together by the strong nuclear force. A single quark cannot exist alone in nature. Pull one quark away from its partners, and the energy required to separate them is so high that it spontaneously creates a new quark pair, rather than allowing the solo quark to escape. Quarks are permanently imprisoned. Scientists call this property confinement. Quarks are the only known particles in the universe that can never be observed in isolation. You can infer everything about them from the particles they form, but you can never catch one by itself. Now, where does the beauty quark fit? The beauty quark, also called the bottom quark, is the 5th of the 6 flavors. It is roughly 4,000 times heavier than an up quark. It is produced only in high-energy collisions, which is why you need something like the Large Hadron Collider to study it in large numbers. When a beauty quark forms during a collision, it quickly combines with other quarks to form a composite particle. That particle then travels a short distance before the beauty quark inside it decays, converting into a lighter quark and releasing energy and other particles in the process. The specific particles released during that decay carry the information scientists need. What types of leptons appear? How often? At what energies? Every detail is a clue about which forces were involved. The standard model has precise predictions for all of it, and as the LHCb experiment showed, some of those predictions are off. But the beauty quark is only one thread. Other anomalies started appearing in a completely different class of particles, ones that have nothing to do with quarks at all, leptons. And one lepton in particular turned out to be the center of the most dramatic anomaly in recent physics. A particle so ordinary, it passes through every person on Earth constantly, every second of every day, without anyone noticing, until it started misbehaving. Most of the Large Hadron Collider's detectors are built to catch as much as possible. LHCb was built to catch one thing. The name stands for Large Hadron Collider Beauty. The experiment is a single-arm spectrometer, which means instead of surrounding the collision point in all directions like a giant sphere, it extends in one direction from the collision, like a telescope pointed at the spray of particles coming out of the crash. This design was a deliberate choice. Beauty quarks do not spray out randomly in all directions. They tend to shoot forward along the beamline at shallow angles. LHCb is positioned to catch them at exactly those angles with maximum efficiency. The detector itself is about 65 feet long and as wide as a school bus. It sits inside a cavern underground, surrounded by layers of different detector types, stacked one after another. The first layer tracks the paths of charged particles as they fly through. The next layer identifies what those particles are. Then come layers that measure energy, followed by the outermost layer that identifies muons, which can penetrate material that stops other particles cold. Each layer tells a different piece of the story. Together, they can reconstruct what happened at the collision point with extraordinary detail, working backward from the debris to figure out which particles existed, for how long, and how they decayed. The key challenge with beauty quarks is their short lifetime. They survive for about 1.5 picoseconds. 1 picosecond is 1 trillionth of a second. During that time, the beauty hadron travels roughly 1/3 of an inch before decaying. That tiny distance is actually measurable. LHCb's first tracking layer is precise enough to detect it. The fact that the particle travels a visible distance before decaying is what makes the whole experiment possible. If beauty quarks decayed instantly at the collision point, their signal would be buried under the enormous flood of other particles produced in every collision. The tiny displacement lets scientists tag them separately. Over the years the experiment has run, LHCb has recorded trillions of collisions and identified hundreds of billions of beauty quark decays. The statistical power of that dataset is enormous. When a deviation appears in such a large sample, even a tiny one, it is highly unlikely to be noise. The team behind LHCb includes over 1,000 scientists from institutions across the world. When a result comes out of that collaboration, it has been checked by hundreds of pairs of eyes using independent analysis techniques. The checks are designed to be adversarial. Team members actively try to find flaws in each other's analysis. Results that survive that process are taken seriously. The beauty quark results survived. And separately, across the Atlantic, a different machine was running a completely different experiment on a completely different particle. A particle with a name that sounds like something from a bad science fiction script, but turns out to be the most precisely measured object in all of physics. Its name is the muon, and what scientists found when they measured it shook the entire field. Physics runs on symmetry, not the aesthetic kind, not the kind you notice when a face looks balanced, the mathematical kind. The kind where swapping one thing for another in an equation leaves the answer unchanged. Symmetry in that sense is one of the deepest organizing principles in all of science. Lepton universality is a symmetry. It says that all three types of leptons, the electron, the muon, and the tau particle experience the fundamental forces in exactly the same way. They carry the same electric charge. They interact with the same forces. The only thing that differs between them is their mass. The electron is the lightest. The muon is about 200 times heavier. The tau is about 3,500 times heavier than the electron. Mass matters for some things in physics, but the Standard Model says mass does not affect how strongly a particle couples to the fundamental forces. All three leptons couple identically. Their decay rates, when mass effects are accounted for, should be equal. Lepton universality has been tested dozens of times across different particle systems. Every test confirmed it. The rules seemed rock solid. When the LHCb experiment started seeing beauty quarks decay into electrons and muons at different rates, it meant lepton universality was being violated. The two types of leptons were experiencing the decay differently. Something in the interaction was treating them differently, despite the Standard Model's guarantee that it should not. The physics community's response was measured but tense. A handful of theorists had actually predicted this could happen, using models that extended the Standard Model by adding new particles. One popular candidate was something called a Z-prime boson, a hypothetical particle similar to the known Z boson, but with different properties, capable of coupling more strongly to one generation of leptons than another. If a Z-prime boson existed, it would insert itself into beauty quark decays. It would act like an invisible thumb on the scale, pushing the decay rate toward electrons and away from muons, or vice versa. Its effects would be subtle, showing up only as a statistical deviation across many millions of decays. Exactly the kind of deviation LHCb was seeing. Other theorists pointed toward a different candidate called a leptoquark. A leptoquark is a hypothetical particle that connects quarks and leptons directly. In the Standard Model, quarks and leptons are completely separate families with no direct interaction. A leptoquark would bridge that gap, creating a new pathway for quarks to decay into specific leptons more than others. Either candidate would be a particle beyond the Standard Model. Either one would require rewriting significant portions of fundamental physics. Neither has been directly detected, but the signal pointing toward one of them refuses to go away, and the deeper that signal was investigated, the stranger the picture became. Because lepton universality was only one of the things showing cracks. Another set of experiments, running not at CERN but at a dedicated facility in Illinois, was pushing a completely different particle past its predicted behavior. And that particle, the muon, was already the strangest thing in the lepton family before the experiment started. Muons are falling through you constantly. Right now, as you listen to this, roughly 10,000 muons are passing through your body every minute. They come from above. When cosmic rays, high-energy particles from space, slam into the upper atmosphere, roughly 30 miles up, they produce a cascade of secondary particles. Many of those are muons. They travel downward at close to the speed of light, passing through the atmosphere, through buildings, through you, and into the ground. You cannot feel them. They carry no charge that interacts significantly with your body. They are like ghost bullets, passing through matter with almost no friction. A muon is essentially a heavy electron. It carries the same negative charge. It interacts with the same forces. It behaves in almost every measurable way like an electron would, except for two things. It is 200 times heavier, and it is unstable. A muon only lives for about 2/millionths of a second before it decays into an electron and two neutrinos. 2/millionths of a second sounds short. It is actually remarkable for an unstable particle. Most exotic particles produced in colliders live for fractions of a trillionth of a second. A muon lives long enough to travel from the upper atmosphere all the way to the ground. That is only possible because of time dilation, a real effect of special relativity where fast-moving objects experience time more slowly from the perspective of a stationary observer. The muon ages slowly during its journey because it is moving so fast. By the time it reaches the ground, it has aged only slightly, even though several microseconds have passed in the outside world. Muons experience time differently because they are moving near light speed. That is not a metaphor, that is measured physics. Now, here is the property that makes muons useful to scientists. A muon behaves like a tiny magnet. It has a magnetic moment, meaning it acts like it has a north and south pole and responds to magnetic fields by spinning. The standard model predicts exactly how strong that magnetic moment should be. The number is called G, and the model says it should be almost exactly 2, with a tiny correction from quantum effects. That tiny correction can be calculated with extraordinary precision. The value of G-2 for the muon is one of the most precisely calculated numbers in all of physics. Theorists have spent decades refining the calculation, and it is also one of the most precisely measured numbers. Scientists built an entire experiment at Brookhaven National Laboratory in New York specifically to measure it. Their result did not match the theoretical prediction. The gap was small, but it was there, and it was in the same direction every time they measured. Scientists proposed a simple explanation. Something beyond the standard model was interacting with the muon during its lifetime. Something that added a tiny extra push to its magnetic moment. Something invisible to the model, but real enough to show up in the measurement. They called it a new physics signal, and they decided to confirm it with a better experiment. The machine they built for that confirmation, in the flat fields of Illinois, produced a result that changed the conversation entirely. The experiment required moving a 50-foot wide magnet from New York to Illinois without tilting it more than a fraction of a degree. The magnet weighs 17 tons. It is a ring of superconducting coils that produces a magnetic field of extraordinary uniformity. Scientists spent a year planning the move. They could not tilt it because the internal coils, built over decades, would shift out of alignment. They could not fly it because no aircraft could handle the geometry. They could not cut it apart and reassemble it because any weld would introduce imperfections. They drove it, slowly, on a custom-built transport vehicle, along a route that avoided highway overpasses and sharp turns. The journey from Brookhaven National Laboratory in New York to Fermilab in Illinois took about 35 days. Scientists tracked it in real time. Crowds of people came out to watch it roll through their towns at 3 miles per hour in the middle of the night. It arrived without incident. Scientists spent years setting it up inside a new facility at Fermilab, calibrating every component, testing every measurement system. Then they fired it up. The experiment works like this. Scientists produce muons inside a small accelerator, shoot them into the big magnet ring, and let them circulate inside the magnetic field. As muons travel around the ring, their spin precesses, meaning it wobbles like a spinning top. The rate of that wobble depends on the muon's magnetic moment. Measure the wobble rate, and you measure G-2. The field inside the ring is controlled with such precision that temperature changes of less than 1/1000th of a degree Fahrenheit would affect the result. Vibrations from traffic outside the building are monitored. The orientation of the Earth's magnetic field is accounted for. Scientists track every variable that could possibly affect the measurement. They collected data through multiple runs. Each run produced results. Each result pointed in the same direction. The muon's magnetic moment was higher than the standard model predicted, the same direction as the Brookhaven result. A stronger deviation. Across multiple years of data, the combined significance of the result reached 4.2 sigma, close enough to the 5 sigma discovery threshold that the entire physics community started paying close attention. Something was adding energy to the muon's magnetic moment, something that the standard model did not put there. The invisible influence was real enough to show up in measurement, consistent enough to survive years of checking. The team at Fermilab published their result. The physics world responded immediately. Within hours, theorists had uploaded dozens of papers, attempting to explain what the new influence might be. Most of the theories pointed to the same place that the beauty quark anomalies pointed: new particles, new forces, something operating just beyond the edge of the standard model's boundary. Two completely independent experiments, using two completely different methods on two different continents, had now found evidence pointing in the same direction. And then a third result arrived from a completely different part of CERN's program, one that scientists did not see coming, and one that they described, without exaggeration, as a crisis. Science has a trust problem. That sounds like an insult. It is actually a feature. Scientists do not trust single results. A single experiment can have a hidden flaw, a biased analysis, a subtle equipment problem. Science requires independent confirmation. The same result produced by a different team using a different method on a different machine. When two independent experiments agree, the probability of both being wrong in the same way drops enormously. When they disagree with the same prediction in the same direction, that is when physicists start changing their plans. The Brookhaven G-2 experiment produced its result in 2001. Scientists at the time did not have a Fermilab facility ready to confirm it. For nearly 20 years, that result sat in the literature as an intriguing anomaly, strong enough to take seriously, isolated enough that some physicists assumed better measurements would eventually explain it away. Fermilab did not explain it away. Fermilab made it louder. The Fermilab machine is the same magnet, same design, same physical measurement principle as Brookhaven, but the facility was built with improvements. The beam of muons is more intense, producing more events per hour. The detectors are more precise. The calibration systems are more sophisticated. The analysis teams used blinded analysis, meaning they did not look at the final number until all other checks were complete, specifically to prevent unconscious bias from affecting the result. Every improvement was aimed at reducing the possibility that the deviation was an artifact of the measurement. The deviation did not shrink. It held steady and then grew as more data came in. When scientists combined the Brookhaven and Fermilab results, the combined significance exceeds 5 sigma. That threshold, 5 sigma, is the conventional standard for claiming a discovery in particle physics. It means the odds of the deviation being a statistical fluke are less than 1 in 3.5 million. The scientific community is careful about what that means. 5 sigma significance does not automatically mean a discovery of new physics. It means the deviation is real. It means something is happening that produces a muon magnetic moment higher than the prediction. The debate is about what that something is. One explanation is that the theoretical calculation of the standard model prediction has an error. Calculating G-2 requires summing contributions from enormous numbers of quantum processes. Each contribution is small, but they add up. If any of the theoretical inputs are slightly wrong, the prediction shifts. A group of theorists calculated a specific set of contributions called hadronic vacuum polarization using a new technique in 2021. Their result shifted the theoretical prediction closer to the measured value, reducing the apparent discrepancy. The physics community debated vigorously whether the new calculation was more accurate than the older method. The debate is not resolved. Some theoretical approaches favor a smaller discrepancy, others favor the original larger one. But even under the most favorable theoretical scenarios, a meaningful gap remains. And across all the anomalies taken together, beauty quarks, muons, lepton universality, the pattern keeps pointing the same direction. Something the standard model cannot account for is leaving fingerprints across multiple experiments. What that something is, the physics community has a name for it, and that name carries consequences so large that discovering it would be one of the most significant moments in the history of science. The phrase sounds exciting and vague at the same time. New physics. Scientists use it as a catch-all for any result that cannot be explained by the standard model. It is a placeholder, a label for the unknown, and it shows up in physics papers constantly right now, attached to every anomaly CERN and Fermilab have found. But what does it actually mean? The standard model describes 4 fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. It describes the particles that carry those forces and the particles that feel them. It tells you how they interact, how fast, in what proportions. Everything the model covers, it covers with extraordinary precision. New physics means a fifth force, a new particle, a new field, or a new principle that the model has no slot for, something that exists and operates in the universe but falls entirely outside the current framework. The last time physics encountered something like that was the discovery of the weak nuclear force in the mid-20th century. Before that discovery, scientists knew about gravity and electromagnetism. The weak force, the force responsible for radioactive decay, was a completely new category of interaction that required new mathematics, new particles, and a significant expansion of the theoretical framework. Finding new physics now would be bigger. The standard model is more complete than what existed before the weak force was understood. Any addition to it would represent a genuine expansion of the map of reality, and the implications reach far beyond particle physics. The standard model cannot explain dark matter. Whatever dark matter is, it is not any particle the model describes. A confirmed piece of new physics from the muon anomaly or the beauty quark results might share properties with dark matter candidates. It would not automatically identify dark matter, but it would tell scientists where to look. The model cannot explain the matter-antimatter asymmetry in a complete way. New physics, capable of producing a larger charge parity violation, could fill that gap. It could explain why the universe is full of matter instead of empty. The model cannot explain why the Higgs field has the strength it has. The Higgs boson mass requires an enormous amount of fine-tuning in the model's equations, like a dial set to an impossibly precise value for no obvious reason. New physics could provide a natural mechanism that explains why the dial is set exactly where it is. Every open question in fundamental physics is waiting for the same answer, an answer that exists outside the current model. The anomalies at CERN and Fermilab are the closest thing scientists have found to a crack in the wall, a place where something on the other side is pushing through. What is on the other side has names. Theorists have been building models of it for decades. The most elegant of those models predicted not just new particles but entire new symmetries of nature, doubling the known particle catalogue in one move. Scientists built the Large Hadron Collider partly to test that model. They searched for it for years after the Higgs discovery. They did not find it, and the failure to find it turned out to be almost as important as the anomalies themselves. Supersymmetry is the most elegant solution to the standard model's problems that anyone has ever proposed. It is also one of the most persistently absent. The idea is simple on the surface. The standard model divides particles into two families based on a quantum property called spin. Particles with half-integer spin are called fermions. They make up matter. Quarks and electrons are fermions. Particles with whole number spin are called bosons. They carry forces. Photons and gluons are bosons. Supersymmetry proposes a perfect symmetry between these two families. Every fermion has a corresponding boson partner, called a superpartner. Every boson has a corresponding fermion partner. The electron's superpartner is called the selectron. The quark superpartner is the squark. The photon's superpartner is the photino. None of these superpartners have ever been observed. Supersymmetry predicts that every superpartner should be heavier than its standard model twin. That is why they have not been observed in normal conditions. They would only appear in high-energy collisions. The Large Hadron Collider is exactly the kind of machine that should be able to produce them. Scientists at CERN searched for superpartners after the Higgs discovery in 2012. They ran millions of collision events, looking for the signatures that superpartners would leave. They found nothing. They increased the collider's energy and searched again. Still nothing. They ran more data. Nothing. They pushed the minimum mass limit for superpartners higher and higher based on non-detection. Some of the lightest predicted superpartners, which should have been easiest to find, are now known to be heavier than several hundred times the proton mass, if they exist at all. The region of parameter space where supersymmetry is most natural, where it would solve the standard model's problems most cleanly, has been almost entirely ruled out. This is called the naturalness problem. Supersymmetry was supposed to be the natural solution. Finding no superpartners in the natural mass range means either they are hiding at masses so high that the Large Hadron Collider cannot reach them, or supersymmetry does not exist in the form theorists expected. The physics community's response has been uncomfortable. Supersymmetry is mathematically beautiful. It unifies the particle families in a way that feels deep and satisfying. Many physicists spent decades building their careers on it. Watching the Large Hadron Collider find nothing, run after run, has been genuinely painful for those researchers. But the data is the data, and science does not negotiate with beautiful theories. Supersymmetry might still be real. Its superpartners might exist at energies the current collider cannot reach. A larger machine could change that. But right now, supersymmetry is a theory under enormous pressure. And if supersymmetry is not the answer to what the anomalies are pointing at, another candidate steps forward, one that connects directly to the most mysterious substance in the universe, the invisible mass that holds galaxies together, the thing that makes up most of the universe's weight, the thing no one has ever directly detected. Everything you can see is a minority. Stars, planets, gas clouds, galaxies, all the visible matter in the universe adds up to about 5% of everything that exists. Another 27% is something scientists call dark matter. It does not emit light, reflect light, or absorb light. It cannot be seen by any telescope ever built, but it has mass, and mass produces gravity, and gravity can be measured even when its source is invisible. Scientists first suspected dark matter in the 1930s, when a Swiss astronomer noticed that galaxies in clusters were moving too fast. The gravitational pull from the visible matter alone was not enough to hold them together at those speeds. There had to be more mass than anyone could see. Decades later, measurements of how galaxies rotate confirmed it. Stars on the outer edges of galaxies orbit just as fast as stars near the center. Under normal gravity, outer stars should move slower, the way planets farther from the sun take longer to complete their orbits. The fact that they do not means something is providing extra gravitational pull throughout the entire galaxy, something massive, spread out in a vast invisible halo around every galaxy. That something is dark matter, and no one knows what it is. The standard model has no particle that fits the description. Dark matter interacts with gravity. It does not interact with electromagnetism, which is why it is invisible. The model has no candidate particle with those exact properties. None. One class of theoretical dark matter candidates is called weakly interacting massive particles. The name is a description. They have mass, they interact through the weak nuclear force, and they do not interact electromagnetically. These particles would be invisible, pass through normal matter with rare interactions, cluster gravitationally, and naturally produce the right amount of dark matter to match what we observe in the universe. Here is where CERN enters the picture directly. Weakly interacting massive particles, if they exist, would be produced in high-energy collisions. The Large Hadron Collider produces exactly those collisions. Scientists have searched for them in collision data repeatedly. So far, no confirmed detection, but the anomalies change the picture. If a new particle exists that is causing the beauty quark deviations or the muon magnetic moment discrepancy, it must have properties that put it outside the standard model. Some of those properties overlap with what dark matter candidates are expected to have. A particle that couples differently to different generations of leptons, for example, would be a new kind of force carrier. That force carrier might also interact with dark matter particles, linking the two mysteries. Scientists do not have a confirmed connection. It remains a theoretical possibility. But multiple research teams have built models where the same new particle explains both the flavor anomalies at CERN and the dark matter density of the universe simultaneously. If such a particle exists and is found, it would solve two of the biggest open questions in physics at once. The search for dark matter at CERN runs in parallel with every other analysis. Detectors watch for signatures of particles that appear in a collision and then vanish without leaving a trace. A particle that does not interact electromagnetically would do exactly that. It would carry energy away from the collision point invisibly, leaving a gap in the energy budget that detectors would register as missing energy. Missing energy events happen at the Large Hadron Collider constantly. Most have mundane explanations. A small fraction remain unexplained after all other possibilities are ruled out. That small fraction is where scientists spend a great deal of their time. And the anomalies suggest that whatever is causing the flavor violations might be leaving its own version of that gap, a gap that connects directly to the universe's largest unsolved mystery. What that gap connects to next reaches far beyond particle physics into the structure of space itself and into a discovery about the universe's expansion that should have been impossible. The universe is running away from itself. Every galaxy is moving away from every other galaxy. Space itself is stretching, carrying everything inside it apart, like dots drawn on a balloon being inflated. Scientists confirmed this in the early 20th century when they measured the light from distant galaxies and found it shifted toward red wavelengths, the signature of something moving away. That much was expected. The Big Bang implied expansion. What was not expected was what scientists discovered in 1998. The expansion is accelerating. Two independent teams were studying distant supernovae, exploding stars so bright they can be seen across billions of light years. They were using them as distance markers to map the expansion rate of the universe through time. The assumption going in was that gravity would be slowing the expansion down. More matter means more gravity, and gravity pulls things together. The expansion should be decelerating. It was doing the opposite. The universe was expanding faster now than it was billions of years ago. Something was pushing space apart faster and faster over time. Something with enough energy to overcome the gravitational pull of all the matter in the observable universe. Scientists named it dark energy. They have almost no idea what it is. Dark energy makes up about 68% of everything in the universe. Combined with dark matter, the two unknown quantities account for 95% of the universe's total content. The Standard Model, the framework that describes all of particle physics, addresses exactly 0% of that 95. Here is where the connection to CERN becomes direct and unsettling. Dark energy is sometimes modeled as a property of empty space itself, a kind of energy that the vacuum carries naturally. Quantum mechanics predicts that empty space should be full of virtual particles flickering in and out of existence. Those virtual particles carry energy. The energy of the vacuum is called the cosmological constant. When physicists calculate the vacuum energy using quantum mechanics, they get a number. When they measure the cosmological constant from astronomical observations, they get a different number. The two numbers differ by a factor of 10 raised to the power of 120. That is, a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation in all of science. Scientists call it the worst prediction in physics. The fact that the universe is expanding at all, let alone accelerating, is tied to that discrepancy. And the fact that the Standard Model's particles produce virtual fluctuations in the vacuum connects the failure of dark energy theory directly to the same framework, producing the beauty quark and muon anomalies. Something is wrong at the foundation. The anomalies at CERN are cracks in the floor. Dark energy is a crack in the ceiling, and they might share the same underlying cause. Several theoretical frameworks that attempt to explain the muon anomaly also modify the vacuum energy in ways that could affect dark energy. The connection is not confirmed. It is speculative but mathematically grounded. Physicists take it seriously enough to publish on it. If a new particle or force causes the flavor anomalies, and also explains why the vacuum has the energy density it has, the discovery would connect the smallest scale in physics to the largest scale in cosmology. It would bridge the gap between what happens inside a proton and what happens across the entire observable universe. That bridge has never been built. Every attempt to connect quantum mechanics to cosmology at that level has failed. Something in CERN's data might be pointing at how to build it. And the strangest part of that possibility involves a direction most people do not consider when thinking about space. a direction that does not point up, down, left, or right. You experience 3 dimensions of space: left and right, forward and back, up and down. Add time and you get 4 dimensions total, which is the framework physicists use to describe all known events. 4 dimensions account for everything you have ever experienced and everything any instrument has ever measured. The math of theoretical physics does not stop at 4. String theory, one of the leading candidates for a complete theory of nature, requires 10 dimensions to be mathematically consistent. Other versions require 11. The extra dimensions are not science fiction. They are mathematical requirements. If the equations are correct, the extra dimensions must exist. So why do you not experience them? One explanation is that the extra dimensions are curled up so tightly that nothing at ordinary scales can detect them. Imagine a garden hose. From far away, it looks like a one-dimensional line. But zoom in and you see it has width, a circular dimension curled around itself. An ant living on the hose would experience 2 dimensions. You, looking from far away, only see 1. Extra dimensions might be curled at a scale far smaller than an atom, invisible to every instrument ever built. Another explanation is stranger. Extra dimensions might be large, even infinite, but particles of matter are stuck to a 3-dimensional surface within the higher dimensional space, like dust on a table that can slide across the surface but cannot rise off it. In this model, gravity is the only force that leaks into the extra dimensions, which would explain why gravity is so much weaker than the other fundamental forces. CERN is actively testing both possibilities. If extra dimensions exist at a scale the Large Hadron Collider can probe, something remarkable would happen in collisions. Particles would occasionally radiate energy into the extra dimensions. That energy would appear to vanish from the collision, showing up as missing energy in the detectors. Scientists watch for exactly this signature in collision data. A more dramatic possibility is graviton production. Gravitons are the hypothetical particles that carry the gravitational force. If extra dimensions allow gravity to leak into higher dimensional space, graviton-like particles might be produced in collisions and then escape into those dimensions. Their departure would again appear as missing energy, but with a distinctive pattern. Scientists have searched for both signatures. No confirmed detection yet, but the searches have established limits. If extra dimensions exist at scales the collider can reach, they must be curled below a certain size. Each run of the experiment tightens those limits. The connection to CERN's anomalies is theoretical but persistent. Several models that predict the extra-gauge bosons or leptoquarks that could explain the beauty quark anomaly also naturally incorporate extra dimensions. The new particle causing the lepton universality violation might be a residue of physics happening in a higher dimensional space, a shadow cast by something existing in a direction you cannot point to. That idea lands differently than most physics concepts. An extra dimension is not a small thing. It is an entire additional direction of reality, a place particles could travel that is perpendicular to everything you have ever known. If evidence for it appeared in CERN's data, it would mean the universe you inhabit is a surface, a slice, a membrane stretched through a higher dimensional space you have no sensory access to. And floating in that higher dimensional space, there might be forces that reach into your slice from outside. Forces that have been nudging particles and bending physics in ways your instruments are only just beginning to measure. One of those forces has a name scientists have been quietly debating for decades. 4 forces run the universe. Gravity holds planets in orbit and keeps you on the ground. Electromagnetism controls light, electricity, and the behavior of atoms. The strong nuclear force holds the nucleus of every atom together. The weak nuclear force governs radioactive decay and is responsible for the nuclear reactions inside the sundae. 4 forces. Every physical phenomenon ever observed fits inside those 4, but the anomalies at CERN keep pointing toward a 5th. The idea of a 5th force is not new. Physicists have proposed versions of it for decades, every time an experiment produced an unexplained result. Most of those proposals faded when better measurements explained the anomaly without new physics. The fifth force became something of a running joke in the field, a placeholder for wishful thinking. The current situation is different. The anomalies producing the fifth force discussion are not single, isolated results from a single team. They are a cluster of independent measurements from different machines, different particles, different research groups, all showing deviations that point toward the same gap in the standard model. A fifth force would be a new type of interaction carried by a new type of particle, operating on rules the standard model does not contain. Depending on its properties, it might only affect certain types of particles. It might operate over very short distances. It might be extremely weak at energies we interact with in everyday life, showing up only in the precise measurements of particle physics experiments. Several theoretical candidates have been proposed. The Z-prime boson, already mentioned in connection with the lepton universality violation, is one. It would be a new force carrier, similar to the Z boson, that mediates the weak force, but with a different coupling pattern that treats leptons differently based on their generation. Another candidate, proposed after the muon G-2 results, is called a muon-philic boson, a particle that couples specifically to muons much more strongly than to electrons. This would explain why the muon's magnetic moment is higher than predicted. The muon-philic boson would constantly interact with the muon during its lifetime, adding a small extra contribution to its magnetic moment that the standard model cannot account for. Searches for both candidates are underway at CERN and at other facilities. A result from 2023 drew significant attention. Scientists at a laboratory in South Korea, measuring the properties of electrons at low energies, found a small deviation consistent with what a new light boson would produce. The result was not confirmed independently, and the significance level was below discovery threshold. But it added another data point, pointing in the same direction. The fifth force, if real, would slot into the hierarchy of forces somewhere. It might be far weaker than the four known forces at ordinary scales, explaining why it was never detected in everyday experiments. It might operate over distances shorter than an atomic nucleus, making it invisible to anything except high-precision particle measurements. Whatever its properties, its existence would mean the framework physicists have used for 50 years is a subset of something larger. A map that got most of the territory right but missed an entire region. Every few years, a new experiment either strengthens the case or weakens it. Right now, the case is stronger than it has ever been. And the strongest single piece of evidence connecting all of it, the anomaly that stunned even veteran physicists when it arrived, came from a particle measurement so precise it took 40 years of work to complete. For the first millionth of a second after the Big Bang, matter as you know it did not exist. Protons and neutrons had not formed yet. Atoms were billions of years away. Even quarks could not stay bound to each other. The universe was so hot and so dense that quarks and gluons moved freely, a swirling soup of fundamental particles with no structure at all. Physicists call this state the quark-gluon plasma. It existed for an incredibly brief window of time. Then the universe cooled. Quarks slowed down enough for the strong nuclear force to pull them together. Protons and neutrons formed. The soup congealed into structure. The particles of the modern universe were born. That primordial soup has never existed again anywhere in the natural universe. Temperatures required to maintain it are trillions of degrees. No star reaches that temperature. No known astrophysical event sustains it, except inside the Large Hadron Collider. When CERN collides heavy atomic nuclei instead of protons, specifically lead nuclei, the collision releases so much energy in such a small space that the temperature briefly exceeds several trillion degrees. For a fraction of a second, the quarks inside those nuclei melt free from each other. The quark-gluon plasma reappears. A dedicated detector called the Large Ion Collider experiment, built into the same underground ring, observes these collisions. It watches the plasma form and then cool. It tracks the particles that emerge as the plasma congeals back into ordinary matter in real time. What scientists found inside the quark-gluon plasma surprised them. They expected it to behave like a gas. At temperatures that extreme, with particles moving at near light speed, gas-like behavior made intuitive sense. Instead, the plasma flows like a liquid, a nearly perfect liquid, a fluid with almost zero internal friction, meaning particles inside it flow past each other with almost no resistance. It is the closest thing to a perfect fluid that has ever been observed or created. Water has a viscosity, a resistance to flow. Honey has more. The quark-gluon plasma has less viscosity than anything scientists have measured. It flows with an ease that approaches the theoretical minimum allowed by quantum mechanics. That minimum was calculated using a formula from string theory, not from the standard model. String theory, the framework requiring extra dimensions, predicted that the minimum possible viscosity of any fluid is a specific small number. The quark-gluon plasma hits almost exactly that number. The connection between string theory, mathematics, and laboratory measurements of a quark plasma was unexpected. It does not prove string theory is correct, but it suggests that mathematical tools from string theory describe real physical phenomena accurately, which is a significant result on its own. The plasma also reveals something about time. In the very early universe, the transition from plasma to structured matter happened in a specific direction. Matter organized, structure emerged. The entropy, the measure of disorder, increased. That increase defines the direction of time, forward, toward more disorder. Watching the plasma form and cool in the detector is watching that process happen in miniature, and in those observations, scientists found that the plasma does not behave symmetrically in time. Certain processes happen more often in one direction than the other. That asymmetry connects directly back to charge parity violation, the same broken symmetry that allowed matter to survive the early universe. And measuring it precisely inside the plasma adds another data point to the same mystery CERN has been circling from every direction. One specific measurement inside this plasma, involving a particle called the W boson, produced a result so far outside expectations that scientists reached for the word crisis. The number is almost impossible to feel. Several trillion degrees. For context, the center of the Sun reaches about 27 million degrees Fahrenheit. The quark-gluon plasma inside the Large Hadron Collider during a lead-ion collision is roughly 100,000 times hotter than that. No object in the modern universe reaches that temperature naturally. It existed only in the first microsecond after the Big Bang, and then the universe expanded and cooled, and it was gone, until scientists in Geneva decided to recreate it. The lead ions used in these collisions carry 94 protons each, plus over 100 neutrons. When two of them collide at near light speed, the result is not a simple particle collision. It is the simultaneous collision of hundreds of protons and hundreds of neutrons, all crashing into each other, within a space smaller than a single proton's width. The energy density is beyond any other human-made event. Inside that space, for roughly 1/10,000th of a trillionth of a second, the plasma exists. What makes the quark-gluon plasma scientifically remarkable beyond its temperature is what it reveals about the strong nuclear force. That force is normally responsible for confining quarks inside protons and neutrons permanently. In the plasma, it is overwhelmed by thermal energy. Quarks move freely. The confinement breaks down. Watching confinement break and then re-establish as the plasma cools tells scientists directly how the strong force works at its limits. And those measurements have produced results that the theoretical calculations of the strong force do not perfectly predict. The deviations are smaller than the flavor anomalies, but they exist. Even the most well-understood force in the standard model shows cracks when pushed to its extremes. The strong force calculations rely on a technique called lattice quantum chromodynamics. Scientists approximate the calculations by dividing space into a grid and computing the strong force interactions at each point. It is the most accurate method available, but it is still an approximation. The plasma results are pushing the accuracy of those approximations to their limits. One specific result from the plasma experiments involves particles called quarkonia. These are bound states of a quark and its antiquark held together by the strong force. When the plasma forms, the thermal energy disrupts the strong force binding and the quarkonium melts apart. Different types of quarkonium, bound with different force strengths, melt at different temperatures. Measuring which types melt at which temperatures maps the internal temperature of the plasma. The temperature map does not quite match the predictions. The deviations are subtle. Scientists are working to determine whether they reflect errors in the theoretical calculation or physics that the current models miss. If it is missed physics, it means the strong force, the most powerful force in nature, the one that holds every atomic nucleus in the universe together, also has behavior outside its theoretical description. Every force, every particle family, every corner of the standard model that scientists push hard enough shows something the model did not predict. The pattern keeps growing, and one measurement, coming from a completely different part of CERN's program, landed harder than anything else. A measurement that was not a subtle deviation, it was a direct, clean, unambiguous departure from what the model said was possible. It involved the mass of a particle, and mass, in particle physics, is supposed to be one of the things you can calculate exactly. The universe should have ended before it began. When energy converts into matter, it always produces matter and antimatter in equal amounts. Every particle comes with a partner that carries the opposite charge. When those partners meet, they annihilate. Equal production means equal annihilation. The universe should have erased itself in its first second. Something prevented that. The mechanism is called charge parity violation, sometimes shortened to CP violation. Charge refers to electric charge. Parity refers to a symmetry where you flip the spatial coordinates of a process, like viewing it in a mirror. CP symmetry says that if you take any physical process, reverse the charges of all particles involved and mirror their positions, the process should behave identically. Same rates, same outcomes. CP violation means that symmetry breaks. Some processes happen at different rates depending on whether you are looking at matter or antimatter. When matter and antimatter are treated differently by the laws of physics, matter can gain a slight edge. Over vast timescales and enormous numbers of interactions, a tiny edge becomes a decisive one. Scientists first confirmed CP violation in 1964 in a particle called the neutral kaon. The discovery earned a Nobel Prize, but the amount of violation observed was far too small to explain the universe's matter surplus. Physicists went looking for other sources. Beauty quarks became a primary target because the standard model predicted they would show much larger CP violation than kaons. The first beauty quark CP violation was confirmed in 2001. It was larger, and subsequent measurements found more. The LHCb experiment at CERN has produced the most precise measurements of CP violation in beauty quark systems ever made. Each new result refines the picture. The total measured CP violation in beauty quarks is significant, larger than in kaons, and consistent in some channels with standard model predictions. But across all channels combined, a persistent gap remains. The total amount of CP violation measured in all known particles is still far below what would have been needed to produce the observed matter surplus. Something produced more, something that is not in the model. In 2019, LHCb made a separate discovery that pushed the field further. Scientists observed CP violation for the first time in a particle called the D meson, which contains a charm quark. The standard model predicted CP violation would exist there but be tiny, too small to measure with existing technology. LHCb measured it, and the value was larger than predicted. A larger than expected CP violation in a charm meson means the model's calculation of that process is off. Either the calculation has an error, or an additional source of CP violation exists beyond the model's framework. Theorists immediately began building models where a new particle provides additional CP violation in charm quark systems. Several of those same models also predict effects visible in the beauty quark decays already showing anomalies. The threads keep connecting to the same place. CERN is now running with higher luminosity, meaning more collisions per second, producing larger datasets of beauty and charm decays than ever before. Each additional decay is a new measurement. Each additional measurement either strengthens or weakens the case. The case is strengthening, and then one specific number, one precisely measured mass, arrived and changed the temperature of the entire conversation overnight. April of 2022. A team of scientists at the collider detector at Fermilab published a measurement they had spent a decade refining. The paper reported the most precise measurement ever made of the W boson mass. Scientists described it as a tour de force of experimental physics, 40 years of data collection, nearly a decade of analysis, using the most sophisticated statistical techniques in the field. The result came out heavier than the standard model predicted, not by a little, by a gap large enough that if the measurement is correct, the standard model's prediction of the W boson mass is simply wrong. Flat out, incorrect. The W boson is one of the carriers of the weak nuclear force. It has a mass predicted by the standard model with extraordinary precision. That prediction connects to almost every other mass and coupling constant in the model. The W boson mass is deeply embedded in the architecture of the theory. If it is wrong, the error propagates through the entire framework. The Fermilab team's measurement placed the W boson mass at approximately 80,433 mega-electron volts. The standard model predicted it at roughly 80,357 mega-electron volts. The gap is small in absolute terms. In units of measurement precision, it is enormous. The team reported a significance of 7 sigma, nearly twice the 5 sigma discovery threshold. 7 sigma. The probability of a 7 sigma deviation being a statistical fluke is less than 1 in a trillion. The physics community's immediate reaction was a mixture of excitement and caution. A single experimental result, even at 7 sigma, requires independent confirmation before it can overturn 50 years of validated theory. Other measurements of the W boson mass existed, produced by experiments at the Large Electron Positron Collider at CERN in earlier decades. Those measurements were consistent with the standard model prediction. The Fermilab result disagreed with those earlier measurements as well, not just with the theoretical prediction. Scientists began asking whether the Fermilab analysis had a hidden systematic error, a wrong assumption in the analysis pipeline, a miscalibrated detector component, a bias in how the data was selected. The team had checked for all of these. Over years of blind analysis, they found nothing. Other groups began reanalyzing the same raw data using different methods. Some confirmed the central value, others found smaller deviations. The debate continues. Then, in 2023, the Large Electron Positron Collider data was reanalyzed using modern techniques. That reanalysis also produced a W boson mass slightly higher than the standard model prediction, though with a smaller deviation than Fermilab. 2 independent analyses, one historical and one from Fermilab, both pointing above the standard model. An independent CERN measurement, published in 2023, fell closer to the standard model prediction. 3 sets of results, 2 pointing high, 1 consistent with the model, none of them fully agreeing with each other. That level of disagreement between precision experiments is itself extraordinary. Either multiple experiments have correlated systematic errors, which is nearly unthinkable given their independent designs, or the W boson mass is genuinely not where the model says it is. The implications of the latter reach across the entire particle physics framework, and what connects the W boson mass to the other anomalies reveals a pattern that no one has a clean explanation for yet. Measuring the mass of the W boson is one of the hardest experiments in physics. The W boson does not sit still. It does not form a stable object you can weigh on a scale. It appears in a collision and decays in roughly 1/10 of a trillionth of a trillionth of a second. Everything scientists know about its mass comes from the debris it leaves behind. Specifically, from measuring the energies and directions of the particles it decays into, then working backward to calculate what the parent particle must have weighed. The challenge is that those debris particles do not tell the whole story cleanly. When a W boson decays, it produces a lepton and a neutrino. The lepton is detectable. The neutrino passes straight through the detector without leaving a signal. Scientists infer the neutrino's properties from the missing energy in the detector, using conservation of energy and momentum. That inference introduces uncertainty. To reduce that uncertainty to the level needed for a precise mass measurement, scientists need enormous amounts of data, millions of W boson decays. Each one adds a tiny amount of statistical precision. The collider detector at Fermilab ran for decades, collecting data through multiple upgrades and experimental runs. The final dataset used for the 2022 measurement included over 4 million W boson decays. Processing that data required understanding the detector itself at extraordinary depth. Every component of the detector affects how particles are measured: magnetic field strengths, material thicknesses, detector geometry. All of it must be calibrated with precision far better than 1 part in 1,000. The team developed new calibration techniques over years. They used other well-measured particles as reference points, essentially using known masses to tune the instrument before applying it to the unknown. The process was iterative and exhaustive, and the number that came out of all that work was heavier than the model predicted. Here is why that single number matters so much. The standard model's predictions are interconnected. The W boson mass is not calculated in isolation. It is derived from relationships between several fundamental parameters: the strength of the electromagnetic force, the strength of the weak force, and the mass of other particles. Those relationships are precise mathematical identities. If the W boson mass is truly heavier than predicted, one of the other parameters in those identities must also be wrong. Either the electromagnetic coupling, the weak coupling, or something else feeding into the calculation is off. Physicists have measured those other parameters independently and precisely. They agree with each other and with the standard model, which means either several independent, precise measurements are all slightly wrong in a correlated way, or the formula connecting them, the formula that has been the backbone of electroweak theory for decades, has a flaw. A flaw in the electroweak framework is a flaw in the architecture of everything physicists know about how atoms hold together, how radioactive decay works, and how the sun produces energy. It is not a small patch. It is a load-bearing wall. The W boson anomaly did not emerge from a machine no one had used before. It came from the most precisely calibrated detector in Fermilab's history, and it arrived alongside every other anomaly piling up at CERN. Together, they tell a story about a framework built on mostly solid ground, but built on mostly. The corners are cracking, and the cracks keep connecting to the same region of physics, the same gap in the model, the same invisible influence. What gives that invisible influence its most haunting quality is that something very much like it appeared decades ago, quietly, without fanfare, and nobody fully dealt with the consequences. For most of the 20th century, the standard model said neutrinos were massless. Massless particles travel at the speed of light. They carry no weight. They pass through matter with almost no interaction. Billions of them pass through every square inch of your body every second, produced by nuclear reactions in the sun, and you feel nothing. Neutrinos are so weakly interacting that a light year of lead would stop roughly half of them. A light year of lead. That is 6 trillion miles of solid metal. The model predicted 3 types of neutrinos, one paired with each charged lepton: electron neutrinos, muon neutrinos, and tau neutrinos. Each one massless, each one stable, each one locked into its type permanently. Then, in the late 1990s, experiments detected something impossible. Neutrinos were changing type. An electron neutrino produced in the Sun could arrive at Earth as a muon neutrino. A muon neutrino from a cosmic ray could change into a tau neutrino during its journey. The transformation happened spontaneously during travel, as if the particle shifted identity mid-flight. Scientists call this neutrino oscillation. And here is the critical part. Oscillation requires mass. Specifically, it requires that the three types of neutrinos have different masses. If they were all truly massless, oscillation would be impossible. The math is explicit. Massless particles cannot oscillate between types. The discovery of neutrino oscillation confirmed that neutrinos have mass. The Standard Model said they did not. This was not an anomaly in a curve or a slight deviation in a ratio. It was a categorical contradiction. The model said a thing could not happen. The thing happened. Two physicists who led key experiments confirming neutrino oscillation won the Nobel Prize in 2015. The discovery was celebrated as a major step forward, and then physics moved on without fully solving the problem it created. Neutrinos have mass. The Standard Model has no mechanism to give them mass. The model was patched informally by adding mass terms by hand, without explaining where those masses come from. The underlying reason is still unknown. One proposed explanation is a new type of particle called the sterile neutrino. Unlike the three known neutrino types, a sterile neutrino would interact only through gravity. It would not interact through the weak force at all. Completely invisible to every detector. More invisible than even the standard neutrino. Sterile neutrinos are one of the top candidates for dark matter. They would be produced in the early universe, interact gravitationally, cluster into halos around galaxies, and be completely undetectable by any direct measurement instrument. Several experiments have found tentative hints of sterile neutrinos. None have confirmed them. The hints keep showing up and then fading under more precise measurement. A pattern that is frustrating but also revealing. Something is there. It is just outside the reach of current instruments. The neutrino mass anomaly was the first direct experimental proof that the Standard Model is incomplete. It was confirmed beyond any doubt, and yet the model was never truly revised. It was patched, the hole was covered, but the cause of the hole was never identified. Every anomaly at CERN is another hole in the same house. And somewhere beneath all the holes, there may be a foundation problem. Something structural. Something that would explain why these gaps keep appearing in the same corners of the theory. Finding that foundation problem requires something almost no one talks about in public. A machine so large it would encircle an entire city. 3 neutrino types. That is what the Standard Model provides. The electron neutrino, the muon neutrino, the tau neutrino, one partner for each charged lepton. A tidy arrangement that fits neatly into the model's 3-generation structure. But tidy arrangements do not always reflect reality. Experimental hints have been appearing for decades, suggesting a 4th neutrino type exists. Scientists call it the sterile neutrino, named for its refusal to interact through any known force except gravity. While the 3 known neutrinos interact weakly and can be detected by instruments sensitive enough, a sterile neutrino would pass through every detector ever built without leaving a trace. The hints come from an anomaly called the reactor antineutrino anomaly. Nuclear reactors produce enormous numbers of electron antineutrinos as a byproduct of the fission reactions inside. Scientists have measured the flux of those antineutrinos at detectors placed near reactors. The measurements consistently come in below the expected number. Fewer antineutrinos arriving than should be produced. The deficit is small, roughly a few percent, but it is consistent across multiple reactor experiments in multiple countries over multiple years. One explanation is a calculation error in the expected production rate. Teams have been revising those calculations, and some revisions reduce the discrepancy, others do not eliminate it. The other explanation is oscillation into a sterile neutrino. If electron antineutrinos oscillate into sterile ones during the short journey from reactor to detector, the sterile neutrinos would become invisible upon arrival. The count would be low. The more the deficit resembles oscillation math, the more credible the sterile neutrino explanation becomes. A separate anomaly called the gallium anomaly adds weight to the case. Experiments in Russia and the United States used intense radioactive sources to produce electron neutrinos and measured how many a gallium detector captured. The capture rate was consistently lower than predicted by about 20%. 20% is a large and persistent deficit. Again, either the production rate calculation is wrong, which would be remarkable for such well-studied nuclear processes, or something is causing the neutrinos to disappear between source and detector. The oscillation length and energy range for both the reactor anomaly and the gallium anomaly are consistent with each other. They point to a sterile neutrino with a mass roughly 1 electron volt, which is far lighter than even the lightest known neutrino types, but still a real, non-zero mass. CERN has run experiments relevant to sterile neutrino searches. The constraints from the Large Electron-Positron Collider data established that sterile neutrinos cannot mix too strongly with the known types, or they would have been detected. But a weak mixing, just enough to explain the reactor and gallium deficits, is still allowed. A new experiment called the Short Baseline Neutrino Program at Fermilab ran specifically to test the sterile neutrino hypothesis. Preliminary results from 2022 showed some of the anomalous signals weakened under precise measurement. The sterile neutrino remains unconfirmed, but the anomalies have not completely disappeared either. If a fourth type of neutrino exists, it changes the neutrino sector of physics entirely. It would open the door to more types beyond 4. It would provide a new candidate for dark matter. It would explain the matter-antimatter asymmetry through a mechanism called leptogenesis, where heavy, sterile neutrinos in the early universe decayed with CP violation, seeding the matter surplus. The sterile neutrino could solve 3 of the biggest open questions in physics simultaneously. No wonder scientists keep searching, even when each result comes back uncertain. And the particle that might finally confirm or eliminate the sterile neutrino is entangled in one of the strangest phenomena in all of physics. A phenomenon that makes particles aware of each other across any distance in the universe. 2 particles collide at the center of the Large Hadron Collider. They slam together, annihilate, and produce 2 new particles. Those 2 particles fly apart in opposite directions at near light speed. Within seconds, they have traveled miles from the collision point. Within an hour, they have traveled far enough that light itself would take hours to cross the distance between them. And yet, they are connected. Measure a property of one, and you instantly know the corresponding property of the other. Measure the spin of one particle and find it pointing up. The other, no matter how far away, will be found pointing down. The connection does not use a signal. No information travels between them. The correlation just exists, baked into the system from the moment of their shared birth. Einstein called this spooky action at a distance. He hated it. He believed it proved quantum mechanics was incomplete. That hidden information must be traveling between the particles to explain the correlation. In 1964, a physicist named John Bell devised a mathematical test to settle the question. Experiments using Bell's test confirmed, beyond any serious doubt, that the correlations are real and that no hidden information is traveling between the particles. Entanglement is a genuine property of quantum systems. It has no equivalent in everyday experience, and CERN produces entangled particles constantly. Every time the collider creates a pair of particles from the same collision, those particles can be entangled. The beauty quarks, measured by LHCb, produced together from a single decay, carry entangled quantum properties. The measurements scientists make of those decay products are in part measurements of entangled states. This matters for the anomalies in a specific way. Quantum entanglement preserves correlations across distances. When scientists measure one particle in a decay and find a property they did not expect, the entangled partner carries corresponding information. By measuring both products of a decay, scientists can reconstruct the state of the original parent particle with more precision than either measurement alone would provide. Some of the LHCb analyses of beauty quark decays explicitly use entanglement to improve measurement precision. The stronger the entanglement, the tighter the correlation, the more precisely the state of the parent can be reconstructed. That precision is part of why the anomalies survive scrutiny. Entanglement-based analysis reduces certain classes of systematic error that would otherwise muddy the results. Entanglement also plays a role in tests of CP violation. Because entangled particle pairs preserve opposite quantum properties, measuring the decay of one in an entangled pair gives direct information about how the decay of its partner would have proceeded. Scientists use this to test whether matter and antimatter decay identically under identical conditions. When they do not, that asymmetry shows up as a difference in the correlation. The entanglement-based CP violation tests at CERN are among the most sensitive probes of new physics available. Any new force that couples differently to particles and antiparticles would leave a detectable imprint in those correlations. So far, the imprints match the anomalies seen in other analyses. The picture is consistent, and as the picture becomes clearer, some scientists have started asking a question that lives at the boundary between physics and philosophy. If the laws of physics have exceptions, if particles can violate the rules their own model sets for them, what does that say about the rules themselves? What if the rules are not universal? Physicists do not talk about the simulation hypothesis at conferences. Not seriously. Not in peer-reviewed papers. It lives in the space between mainstream physics and the kind of questions that make scientists uncomfortable, because they are not testable, or at least, they were not considered testable until recently. The hypothesis goes like this. If a civilization ever develops the technology to run detailed simulations of physical reality, they would likely run many of them. The number of simulated realities would far exceed the one base reality running the simulations. Statistically, any conscious being is more likely to exist inside a simulation than in the single base reality. If the universe is a simulation, then the laws of physics are the code, and code can have bugs. Bugs are places where the simulation behaves inconsistently with its own rules, places where the output does not match the algorithm, places where something unexpected appears that the underlying code did not put there deliberately. The standard model anomalies fit that description uncomfortably well. A particle should decay one way. It decays another. A mass should be a certain value. The measurement comes out different. The rules say two particle types should experience a force identically. They experience it differently. These are exactly what a programmer would call unexpected outputs. Results that suggest something in the underlying system is not behaving as written. Several physicists have made the argument not as a scientific claim, but as a philosophical observation. If the universe has an underlying mathematical structure, and if that structure is not perfectly self-consistent, the inconsistencies would look exactly like anomalies in precision measurements. You would not see the code. You would only see places where the output glitched. The scientific community's official position is that this kind of reasoning, while interesting, produces no testable predictions and therefore cannot be evaluated scientifically. Science requires experiments that could in principle come out differently depending on whether the hypothesis is true or false. The simulation hypothesis, in most formulations, makes no prediction that could distinguish it from ordinary physics. But one version does. Some theorists have proposed that a simulated universe would show signs of computational structure at very small scales. The fabric of space itself might be discrete rather than continuous, like pixels in an image. Experiments looking for this signature, a minimum granularity to space at the Planck scale, have so far found nothing. What the anomalies genuinely tell scientists, without invoking simulations, is that the mathematical framework describing physics is incomplete. The code, to use that language, has missing lines. Something is happening that the current equations do not account for. Whether that missing something is a new particle, a new force, an extra dimension, or something no one has conceived yet is the open question. And the answer to that question will not come quietly. It will come from a machine. A specific moment when a signal crosses a threshold, a team of physicists looks at a number and everything changes. Understanding what that moment looks like, who decides it is real, and what happens next is its own story. The measurement crosses 5 sigma. A team of physicists inside one of CERN's collaboration rooms stares at a plot on a screen. The peak is there, clean, unmistakable. A new particle, at a mass the standard model has no room for, decaying in exactly the way a Z-prime boson or a leptoquark would decay. The analysis is blinded. That means the team set up all the selection criteria and analysis choices before they looked at the final number, specifically so that nothing about the answer could influence the methodology. The blind analysis is now open. The number is real. What happens next is not an announcement. First, the internal review begins. Within the collaboration, which at CERN includes hundreds to over 1,000 physicists, depending on the experiment, the result gets challenged from every angle. Other groups within the collaboration independently repeat the analysis using different techniques. They look for any systematic effect that could produce a false signal. They simulate fake datasets to test whether the analysis pipeline could manufacture the signal by accident. This process takes months, sometimes over a year. If the result survives, it goes to the collaboration's governing board for approval. Then it is submitted to a peer-reviewed journal. The journal sends it to independent referees, experts who were not part of the collaboration. They scrutinize every step. They ask questions. The authors respond. The process takes more months. While all that is happening, the result leaks. Physics results never stay fully internal. Preprint versions appear online before journal publication. Theorists see them and immediately start building models. Other experiments begin emergency searches for corroborating signals in their own data. The broader physics community begins reacting before any official announcement. The official announcement, when it comes, is typically a seminar at CERN, followed by a press conference. For a discovery as large as a fifth force or a new particle class, the event would be broadcast live. Thousands of physicists would watch simultaneously. Major newspapers would have pre-written draft articles ready to update. The popular press coverage would almost certainly misrepresent the finding in ways that frustrate scientists. Headlines would claim physics is broken or that everything we know is wrong, when the accurate statement is that physics now has a new piece to add. Independent confirmation from a separate experiment would be required before the broad community fully accepted the result. That confirmation could come from Fermilab, from a Japanese experiment called Bell 2, from the upgrade of LHCb, or from a future facility. The time between first anomaly and full community acceptance of a major discovery in particle physics is typically measured in years or decades. The Higgs boson was predicted in 1964 and found in 2012. Neutrino oscillation was hinted at for years before confirmed. The anomalies CERN has now are closer to confirmation than anything at a comparable stage in recent history. But confirmation is not yet here, and getting to confirmation requires something that is not purely scientific. It requires money, political will, and a decision that is being debated right now in rooms far away from any particle accelerator. The Large Hadron Collider costs roughly $1 billion a year to operate. 23 member states fund CERN. The largest contributors are Germany, France, the United Kingdom, and Italy. The budget is negotiated every 5 years in conversations that involve finance ministers, science ministers, and heads of state. Particle physics competes for funding against climate research, medical science, computing infrastructure, and defense. Every time a new budget cycle opens, the case for CERN must be made again. The scientific case is strong. CERN has produced verified discoveries. The World Wide Web was invented at CERN as a tool for sharing data between physicists. Medical technologies derived from CERN's accelerator expertise treat cancer patients. The economic return from CERN's technical innovations has been estimated to exceed its total cost over its history. But the political case is harder. Politicians respond to problems their constituents can see and feel. A discovery in particle physics, however profound, does not appear in daily life. The gap between the work and its consequences is measured in decades or generations. When the Higgs boson was announced in 2012, CERN received a wave of political goodwill. Funding felt justified. The machine had delivered the prize it was built for. That goodwill has a shelf life. The anomalies are compelling scientifically. A muon spinning slightly faster than expected, a beauty quark decaying at the wrong rate, a W boson weighing slightly more than it should. Explaining why those results matter to a finance minister who has constituents asking about hospital budgets is a communication challenge. CERN's leadership is aware of this. The organization spends significant resources on public outreach, visitor programs, educational content, science communication. The goal is to maintain enough public support to sustain political backing through the long gaps between headline discoveries. Right now, CERN is in one of those gaps. The machine is running at higher energy and luminosity than ever before, collecting data that will take years to fully analyze. The anomalies are building, but the definitive result, the 5 sigma confirmation of new physics, has not arrived. If it does not arrive before the next major budget negotiation, the pressure to reduce CERN's funding will be real. Some member states have already signaled that continued investment at current levels requires demonstrated progress toward new discoveries. And there is a deeper tension. The future circular collider, CERN's proposed successor machine, would cost tens of billions of dollars to build. Planning and political approval must begin now, years before the current machine finishes its program. If the future machine is to exist at all, physicists are making the case that the anomalies justify the investment, that the hints of new physics are strong enough to warrant building a machine powerful enough to confirm or deny them definitively. The decision will be made by people who are not physicists, in rooms where equations are not written on whiteboards, and the outcome will determine whether the questions CERN has raised get answered in this century or get left for the next one. CERN has a plan. While the Large Hadron Collider is still running, teams of engineers and physicists are already designing its replacement. The project is called the Future Circular Collider. If built, it would be the largest machine in human history. The tunnel would be 60 miles around. For comparison, the current Large Hadron Collider tunnel is 17 miles around. The new tunnel would encircle the city of Geneva with room to spare, bored through bedrock at depths of up to 800 feet. Inside that tunnel, the machine would accelerate particles to energies roughly 10 times higher than the current collider can reach. At those energies, particles the current machine cannot produce would appear routinely. The machine would generate Higgs bosons by the millions instead of the thousands, allowing measurements of the Higgs field with unprecedented precision. Any new particle with a mass below several tens of thousands of electron volts would be accessible. If the Z-prime boson causing the lepton universality violation exists in the mass range most theorists expect, the future circular collider would produce it in large numbers. If leptoquarks exist, the machine would find them or rule them out entirely. If superpartner particles exist anywhere below the machine's maximum energy, they would show up. The future circular collider would also serve as a factory for W bosons, producing billions of them at precisely controlled energies. The W boson mass controversy would be settled within the first few years of operation, with measurement precision 10 times better than any existing result. The machine is designed in phases. The first phase would be an electron-positron collider using lighter particles that are easier to control precisely. This phase would run as a high-precision measurement machine, testing standard model predictions and the Higgs boson properties at extraordinary resolution. It would take roughly a decade to build and another decade to run. The second phase would use protons, like the current machine, at far higher energies. This is the phase designed for discovery, for finding whatever new physics the anomalies are pointing toward. The total cost estimate is in the range of $15 to $20 billion for the full project, spread over decades. For context, the James Webb Space Telescope cost around $10 billion and took decades from approval to launch. The Future Circular Collider is comparable in scale of ambition and cost. CERN presented the conceptual design report for the project in 2019. An independent panel reviewed the physics case and the technical feasibility. Their report called the project compelling. The European Strategy for Particle Physics, updated in 2020, identified the Future Circular Collider as the highest priority for the long-term future of European particle physics. Formal approval, funding commitment, and construction authorization require agreement from member states. That process began in earnest in 2023 and is ongoing. If approved and built on the current timeline, the first collisions in the electron-positron phase could happen in the late 2040s. The proton phase would follow in the 2050s or 2060s. A generation of physicists now working on the anomalies may not live to see the results from the machine built to answer them. That is the pace of this science. And it raises a question that every anomaly, every unexplained number, every deviation from prediction forces back to the surface. What if the rules of physics are not the same everywhere? Everything science has ever discovered assumes one thing. The laws of physics are universal. The same rules that govern a particle collision in Geneva govern a star exploding in a galaxy a billion light-years away. The same constants, the same forces, the same mathematical relationships hold everywhere in the observable universe. Without that assumption, science as a practice barely functions. You cannot build a model of the universe if the model only applies in your neighborhood. But the assumption has never been fully tested. Scientists have checked the fundamental constants, things like the speed of light, the charge of the electron, and the strength of gravity, across different locations in space by studying distant astrophysical objects. The constants appear consistent. Measurements of light from galaxies billions of light-years away, representing the universe as it was billions of years ago, show physics operating by the same rules it follows here and now. But consistent does not mean identical. The measurements have precision limits. A variation of 1 part in a million in the fine structure constant, the number that governs how strongly electrons interact with photons, would be nearly impossible to detect with current instruments. And the universe is not uniform. Different regions have different densities of matter, different histories, different ages. Some cosmological observations have started suggesting that the constants might not be perfectly stable. A series of measurements of distant quasars, bright cores of ancient galaxies, produced results that some scientists interpret as evidence for a slightly varying fine structure constant. The variation is tiny. The interpretation is disputed. But it exists in the literature as an unresolved question. If the constants vary even slightly across space or time, it changes everything. The standard model would be a local approximation, valid in our corner of the universe and at this moment in cosmic history, but not a fundamental law. The anomalies at CERN might reflect the edge of that local validity, places where the approximation begins to break down, where the constants are pulling slightly away from the values the model was built on. This possibility is deeply uncomfortable because it has no clear solution. If the laws of physics are local, building a more complete model requires understanding why they take the values they do in our region and what they look like elsewhere. That is a problem beyond any machine humans could build. The more grounded interpretation of the anomalies remains the search for new particles and forces. That interpretation is testable. It has predictions. The Future Circular Collider would either find those particles or rule them out at the accessible energy scales. But CERN's results sit at the edge of what humans have ever been able to probe. Each time the machines pushed deeper into the structure of matter, reality turned out stranger than the previous picture suggested. Atoms gave way to nuclei. Nuclei gave way to quarks. Quarks revealed gluons, and a force that confines them permanently. The Higgs field turned out to permeate all of space. Every layer revealed the previous picture was incomplete. The current layer is showing cracks too. Whatever sits beneath those cracks, whether it is a new force, a new symmetry, extra dimensions, or something no theorist has written down yet, it is real, it is measurable, and it is leaving traces in the data of experiments running right now, underneath the French-Swiss border, in a tunnel 300 feet below the ground. The universe is stranger than the rulebook says, and the scientists building the next machine already know it.